Good morning, my name is Max Lear, PhD student at RPI, and I'll be narrating this demo. The work in this presentation is based on a voltage stability method developed by Scott Giosel at RPI, who is currently working for Exponent in New York City. So, let me first give you a general idea of our approach to solve this problem. On this slide, you can see the voltage stability problem, where the west end is the load bus, power generation comes from the east, and the 3 wind farms. The total measured output of the wind farms ranges from 0 to 300 megawatts. Voltage and power flow measurements of the system were provided. Our model includes the power system between the east and west ends and the 3 wind farms. A key part of the method is to estimate the Thevenin equivalence of the east and west ends, based on real-time loading conditions. The PQ capability of the wind farms are modeled accurately. We use the new AQ bus method to compute the voltage stability limit. The question is, given the real-time load condition at the west end, how much more wind power can be accepted into the system before voltage collapses? Looking at the wind output power variation, which was quite fast, we decided that it would be feasible to compute the voltage stability limit once every 30 seconds. Even though we can stop the simulation if voltages go outside 5% of 1 per unit, we'll compute the PV curves as far as the AQ bus method will allow. With 10 minutes of data, the PV curves will be computed 20 times. This problem is quite a difficult one because there are 2 voltage stability limits, one for power delivered to the load, or west bus, and the second for the wind farms to export their power. We will show the voltage stability limits in the execution of our AQ bus voltage stability program. Now, let's see the execution of our voltage stability program. Overall, the user interface is quite simple. To start the program, press the Start button and select the data with which you want to run, which in this case is test case 1. This program consists of various plots of power flow and voltages in the top row, where we have the west end, the wind hub, and the east bus up here for the power flows, and the voltages over here. The Thevenin equivalents are calculated down here with the Thevenin reactance and the Thevenin voltage. Over here, you can see the maximum power output and the current wind output seen in blue. Over here, you see the voltage stability margin. On these 3 graphs down here, you see the PV curves generated for the west substation, the wind hub, and the east substation. The margins are computed every 30 seconds. The red line seen here on the PV curve is the short-term voltage stability margin with no capacitor switching. And the black line seen here shows the long-term voltage stability margin, allowing the shunt capacitor to come on. The green curve shows the PV curve of the wind turbine operating at unity power factor. You see that the AQ bus method can continue beyond the point of voltage collapse. The maximum power transfer to the west end is also shown, which is seen here in black. You can see the ability to deliver power to the load on the west bus varies between 4 and 500 megawatts. On the other hand, the maximum power output of the wind farms is limited by the load. When the load is low, over here, we can see that the wind farms can be the sole power provider, resulting in a high power output limit, seen here. When the load is high, the wind power output is limited by the flow that is already there from the east bus, which is why you see lower values over here. When we see the capacitor switch on at 247.8 seconds, we can see the short and long-term curves start to be equal, which is what we would expect to see. One of the main things of this program is that we can look at any period, every 30-second period, and look at the PV curves for those 30 seconds. So say we want to look at the first PV curve. What we do is we click over here and select the first PV curve. Now we can see this compared to any other 30-second interval on any of these values that we would want to look at. Say we also want to look at when the capacitor turns on, which is point number 9, you can see that PV curve as well. So that is our program. We would like to acknowledge the funding support of NSF and DOE for the current ERC, and in particular for the funding provided by CERTS. We also benefited by a collaboration with BPA engineers. We will appreciate getting any comments from you, the audience. We will be around if you want to learn the details of this work. I'd like to thank everybody for watching our video, and everybody have a great day.